Hello everyone. In this presentation, I'm going to talk about the aeropropulsive test problem we developed that involves coupling CFD simulations with a propulsion model. The main motivation for this problem is the boundary layer ingestion technology, which is a coupled aeropropulsive concept. On the top, you're seeing a reference podded configuration where the propulsion system is separate from the airframe, and on the bottom, you're seeing a boundary layer ingestion configuration where the propulsion system is integrated to the airframe. And the portion of power savings is achieved through minimizing losses in the wake, as you can see in the wake profiles. But the introduction of the BLI technology creates this coupled aeropropulsive design problem. And to study BLI, we've been performing aeropropulsive design optimizations of the Stark ABL configuration over the past year. And what this work has showed us is that performing aeropropulsive design optimizations are still very challenging. There are several ways the CFD model can be coupled to the propulsion model, and different flight conditions require different coupling approaches. So we realized that we needed a simple test problem to study various coupling approaches. And in this presentation, I'm going to talk about the problem formulation we came up with, the CFD and the propulsion models, the 3 levels of difficulty we designed, and the reference implementation. And to start with, the reference test problem must have the basic structure to represent the physics. The goal is to optimize the coupled aeropropulsive system design, and the aerodynamics discipline relates the flow field to forces, and then the propulsion discipline computes the power requirements, and the two disciplines affect each other. So the most basic test problem that we thought of is a podded fan, which has all of these basics and introduces the challenge that we see in aeropropulsive design problems. With this problem, we minimize the shaft power required at a target net thrust. And this aeropropulsive optimization formulation brings in the fundamental challenges in coupling aerodynamics and propulsion. This problem is relevant to academia because even the most straightforward coupling approach is extremely challenging, and it's relevant to industry because this design technology will enable the design optimization of systems that use BLI. And now I'm going to introduce the CFD models we developed for this problem. We have two variants of the podded fan. On the left, you're seeing the actuator zone model where we add body force terms into the volume cells that are inside this fan. And on the right, you're seeing a version that uses powered boundary conditions at the fan face and fan exit to create the effect of the fan on the flow. And the primary aerodynamic design variable we have is the thrust applied to the fan. And this thrust can be directly prescribed with the actuator zone model that's equal to the total thrust you add over the whole volume of the fan. For the power boundary condition model, though, you need to solve 3 conservation equations to get a balanced solution. And that is mass flow going out of the fan exit must be equal to mass flow going into the fan face. Momentum flow going out of the fan exit must be equal to the momentum flow going in plus the thrust we add. And then the energy out of the fan exit must be equal to the energy going in plus the energy added due to the thrust term. And even at this level, the two CFD models provide 2 difficulty levels. And if we just looked at the CFD model, the energy increase across the CFD fan provides an ideal estimate to power where we don't have any losses due to the fan. And the power required to operate the fan can be estimated using the rate of energy added to the flow going through the CFD fan. And the RANS CFD model uses isentropic relationships, which is not enough to model non-ideal losses. So therefore, we need to couple the CFD model to a propulsion model to calculate accurate power requirements. And that brings me to the propulsion model. In this work, we use pyCycle to compute the shaft power required to operate the fan, which is a one-dimensional propulsion model that accounts for the non-ideal losses in the fan. Once the flow conditions are obtained from the CFD model, the propulsion model uses a simple compressor model to compute this shaft power requirement. And we can use several methods to couple the aerodynamics to the propulsion model, which brings me to the 3 levels of difficulty we designed for this problem. On the easiest level, we have a feed-forward coupling from the CFD to the propulsion model. So at the top level, you have the optimizer driving the design, and you go through geometry and then mesh warping module. Then you converge your CFD simulation at the prescribed fan thrust. Now you extract the integrated quantities out of your CFD simulation, and this flows into the propulsion model to compute the shaft power requirements. And the the important part of this formulation is that the outputs of the propulsion model do not affect the CFD model. So this is purely a feed-forward coupling where you can converge both of these analyses separately. And this approach yields reasonably accurate estimations to power requirements at cruise-like conditions where the non-ideal losses are negligible compared to the shaft power required to operate the fan. And this is the formulation we used to optimize the Stark ABL design, but it was still extremely challenging. On the medium level, we add the feedback coupling between the two models, where the non-ideal losses computed in the propulsion model now affect the fan model that we use in the CFD model in terms of heat addition. And the introduction of feedback coupling now creates a requirement for an additional nonlinear solver over these two models, where we need to converge the coupled aeropropulsive analysis. And after converging the aeropropulsive analysis, we also need to converge a coupled adjoint system to obtain derivatives across this model. And the inclusion of previously neglected fan losses in the CFD model enables accurate computations even at off-design conditions, where these non-ideal losses are not negligible compared to the baseline shaft power requirements. And in this formulation, both the CFD model and the propulsion model will converge to the same shaft power requirements. On the hard level, we do not introduce any new aeropropulsive coupling methods, but we extend the single point optimization to a multi-point optimization with on and off design analyses. On the top, as you can see, you still have the optimizer driving the design, and after the mesh warping, first we need to converge our on design analysis. And this block in itself represents a coupled aeropropulsive system. Once we converge this and get the properties of the propulsion model, then we can move on and analyze design at multiple off design conditions, and we can use some constraints from these off design conditions to create a more reasonable design. And this formulation creates a feed forward coupling between the on and off design analyses, where the on-design analysis must finish before the off-design analyses start at every design iteration. So this breaks the commonly used, embarrassingly parallel structure of multi-point optimizations, where we could simulate every point simultaneously. Now, with this formulation, we first need to converge a single on-design point before we can move on to any of the off-design analysis points. And the combinations of on and off design flight conditions closely represent a real design problem. We can include constraints like fan face distortion at high angles of attack using an off design flight condition, and we can perturb the flight conditions near cruise to get a better estimate to power requirement at slightly perturbed flight conditions. To summarize the levels of difficulty we introduced, we have 3 levels of difficulty in terms of coupling, the aeropropulsive coupling, and at least 2 different CFD models to do this. For the aeropropulsive side, we have the easy level, that is a feed-forward coupling from the CFD to the propulsion model. We have the medium level, where there's a two-way coupling between the CFD and the propulsion model. And then the hard level uses a multi-point optimization that represent a real design problem. And for the CFD models, we currently have an actuated region model where you add axial body forces to the volume cells inside the fan. And we have a powered boundary conditions version where we use boundary conditions for the fan face and fan exit to create the effect of the fan on the flow. And I say at least 2 CFD models because these can be extended. We can use more sophisticated actuated zone models that include torque, or we can go to a higher fidelity to model the fan. And now I'm going to talk about our reference implementation. And for this, we use the OpenMDAO Multi-Physics package, or MPhys. MPhys provides the OpenMDAO model structure required to build complex models using high-fidelity simulations. Computational performance and parallelism comes built in with MPhys, and for more details, you can check out my other presentation where you can find details below. And for the models themselves, we use ADFlow as the CFD solver and pyCycle for the propulsion model. The geometry is modeled with OpenVSP, and all of the tools I've described so far are open source. The results can be compared to our previous optimizations of the Stark ABL configuration, and the reference implementation is currently under development, but the plan is to make that open source as well. And for the optimization problem formulation, we minimize the shaft power required for the fan at a target net thrust and fan pressure ratio values. So the objective function is the shaft power computed by the propulsion model, and we have a number of constraints, including the fan pressure ratio target, the net thrust target, and a fan face Mach number target. And on top of these, we have geometric thickness constraints. And we optimize the design using design variables. We optimize the design by changing the fan thrust and the geometric design variables. And with these optimizations, we target combinations of 3 net thrust and 3 fan pressure ratio values. Because the propulsion systems are sized by factors that we do not consider in these optimizations, it is useful to get a range of designs that cover a wide design space so that we can get the trends across this design space. So below, you can see the target net thrust and fan pressure ratios we have for a total of 9 optimizations. In this slide, I'm just showing a sample optimized design at a net thrust of 12 kilonewtons and a fan pressure ratio of 1.3. On the left, you're seeing the initial design, and on the right, you're seeing the optimized design, and the contours reflect the total pressure with respect to the free stream. And there's not much information to be gathered from this plot, but I'm only showing this to represent the range of geometric changes that we expect from these optimizations. Like I said, we're still working on developing the reference implementation, and our near-term plans include using a CAD-based geometry parameterization using Engineering Sketchpad. We will create a family of meshes for multi-level optimizations and for grid convergence studies. And we're working on the medium and hard levels of aeropropulsive coupling, as well as the powered boundary condition version. And to wrap things up, aeropropulsive design optimization is extremely challenging. Even the easy aeropropulsive problems are very difficult. And in this presentation, we introduced 3 levels of test problems with increasing difficulty, with the end goal of a fully coupled propulsion system design. And progress in a propulsive design technology will enable further development of the BLI technology. And hopefully with these advancements, we can see concepts like the Stark ABL in the skies soon. This was the main technical content of this presentation. Thank you for listening. You can join the Q&A session that is under the cognitive discussion, establishing shared MDO test problems for research use. You can find the open source tools I've used in this work, and this work was funded by the NASA Transformational Tools and Technologies and Advanced Air Transport Technology projects. Thank you.